All right, so today we are looking at predicting which way an equilibrium will shift. And we will be doing this using a tool called Q, which stands for the reaction quotient. You should also be aware that this is sometimes called a K-trial because we're trying out something but we're not sure we're at KEQ, or trial KEQ for the same reason. In problems of this type, you will be given concentrations of both the reactants and the products. So you're not necessarily going to know which way it is going to shift. And these concentrations, sorry, I didn't mention it, are not equilibrium concentrations, not equilibrium concentrations. So it's not simply take the four concentrations and stick them into, oh my God, I need to start this over. I'm rambling. In 5, 4, 3, 2. All right, this is worksheet 2.3D, and we are looking today at Q, which is a tool we will use to tell which way an equilibrium will shift. In problems of this sort, you're going to be given concentrations of both the reactants and the products. However, these are not going to be equilibrium concentrations. So we're going to be wondering, which way does the equilibrium shift? We don't know which side in our rice table to put the pluses on and which side to put the minuses on. And this is going to help us figure out which side to put them on. Before we go on, I should mention that Q stands for reaction quotient, and it is identical to the KEQ, except for instead of using equilibrium concentrations, we are going to use initial concentrations. So, whereas KEQ for this system here, we would be using our equilibrium concentrations of all the substances. If we are doing Q, we are using initial concentrations of all the substances. Q can also be called the K-trial because it's like we're trying out something and seeing how it relates to the KEQ, or it can be called the trial KEQ. Now, how does this all work? Well, Q is like the Goldilocks of equilibrium. It can either be too big, it can be too small, or it can be just right. And by telling which of these things it is, we can tell which way the equilibrium is going to shift. So for example, and I don't like the text I've gotten here, but we're going to try and work with it anyway, since it is here. If Q is bigger than KEQ, that means that the ratio of products to reactants, which is what Q and KEQ both are, that means that the products to reactants ratio is too big. And if it's too big, that means we have too much product. Because if this number is too big, that means that the numerator has to be a big-ish number, in fact, a too big number. And if we have too much product, we are going to have to shift to the reactant side to get rid of some of that product. So the system has to shift left, or maybe it's even easier to say to the reactants, or you could even say away from the products. Until, to produce more reactant. Like I said, I'm not thrilled with this fill in the blank nonsense. Until the product to reactant ratio equals KEQ. All right. Now, if Q is smaller than KEQ, what that means is that our current ratio of products to reactants is too small, which means we don't have enough, there's not enough product. So the system is going to shift towards the products, or you could say to the right, to produce more products until the ratio of products to reactants equals KEQ. Now, if Q is equal to KEQ, that means the ratio of products to reactants is just right. And if that's the case, the system is at equilibrium. Okie dokie. So let's try some problems of this sort, and we'll see how this goes. If we've got this reaction here, and if we start with 4 molar CH4, 2 molar C2H4, and 3 molar H2, which direction will the reaction proceed to reach equilibrium? Well, the first thing to realize is that we are given all 3 substances, but if it's asking which direction will the reaction progress to reach equilibrium, what that means is that we are not at equilibrium yet. So all these concentrations here, these are all equilibrium concentrations. No initial concentrations. And anytime you're asked which direction you will shift, you are going to use a Q. So let's write a Q expression for this. So Q, we write it just like KEQ. We take our products, C2H2, and H2 cubed, divided by our reactants, CH4 squared. But before we carry on, I'm going to make sure that I put little I's down here, representing that these are my initial concentrations, because Q uses the initial concentrations. Plugging in our values, C2H2 is 2 molar, 2.00, and H2 is 3.00 molar, and CH4 is 4.00, and that one I have to square, and I forgot to cube my hydrogen, so I'd better do that before I carry on. And I'm going to plug those in my calculator. 2 times 3 cubed divided by 4 squared equals 3.375. So, number 1, find Q. Done. Number 2, you are going to compare Q to KEQ. And so we're going to write out our Q, which is 3.375. And it's really nice if you can show it this way. You can say, you've got your Q here and you give me the value. And then we're going to compare it with KEQ, which is, it should be given in the problem somewhere. Is it? Let's go back and look. There it is up there, 0.154. So KEQ is, whoops, 0.154. And what that means is that Q is bigger than KEQ. Remember that Q and KEQ are both products concentration over reactants. And if Q is bigger than KEQ, then this ratio is too big, which means we need to make the numerator smaller and the denominator needs to get bigger. That'll make the number smaller. So we're going to shift away from the products towards the reactants. Oh, pen, hello. Shift away from products towards reactants. And so that means we are shifting products to reactants to the left. And all you actually need to write, you don't need to write all of this business here. I find it helpful for my own thinking to do that, but all you really need to write is Q 3.375 is greater than KEQ 0.154. Therefore, the reaction shifts left. But like I said, I would find that leap of logic to make a little fast for me and my slow thinking little brain. So I like to write down all the other stuff. It just kind of keeps my head going where it needs to. Okay, and I would box that as my final answer. Okay, let's try another one. And this one is going to require us, we have a, oops, where'd that go? We have a 5-liter flask, which means that my concentrations are not trivial. I don't have a 1-liter flask, so my math is not trivial. So I'm actually, before I do anything else, I'm going to calculate the concentration of SO2, and I'm going to write it down, and I'm going to write down that I'm finding the initial concentration, and that is 0.035 moles, which we're getting from here, divided by 5.00 liters, and that is 0.035 divided by 5 is 7 times 10 to the negative 3, 7.0 times 10 to the negative 3. Our concentration of SO2 Cl2 is, we have 0.5 moles per 5.00 liters, and that is equal to 0.100 molar. Oh, I should have put molar over here, shouldn't I? And I should not forget that I am showing my calculation of my initial concentration of SOCl2. Finally, 0.080 moles of Cl2, so we're finding a concentration of Cl2 initially I. 0.080 moles divided by 5.00 liters equals 0.08 divided by 5 equals 0.016 molar. All right, what is Q equal to? How much space do I have? I've got enough space, lots of space, good. Q is equal to products, SO2, concentration of SO2, initial, times Cl2, Cl2 initial, divided by our reactant, SO2 Cl2 initial. And don't forget square brackets here because we are representing concentrations. What are we going to put our numbers in? We are going to put our numbers in round brackets. So yes, when we substitute it, SO2 becomes 7.0 times 10 to the negative 3, Cl2 0.100, and oh, that's not Cl2. I wrote the wrong one. Cl2 is 0.016. That's better. And my SOCl2 is the one that is 0.100 molar. Plug that in and we get times 7E3 negative divided by, oops, I pressed all clear, 7E3 negative times 0.016 divided by 0.1 equals 1.12 times 10 to the negative 3. And if you'll notice, our KEQ is not in scientific notation, so I am going to rewrite this as 0.00112 just for ease of comparison. So Q is, Q is 0.00112. And we're going to compare that with KEQ, which is, if I recall correctly, 0.078. Yes, 0.078. And that tells us that Q is smaller than KEQ. Therefore, ratio of products to reactants is too small. Therefore, we need to shift to make this number bigger. So we want more stuff in the numerator and less stuff in the denominator. Therefore, must shift to the products. And that's i.e. shift right. Reactants goes to products. All right. And I could even box that whole thing if I wanted to. I could rewrite it if I want to, but I do not have to. Okay, next. This one is, we're actually going to take it a step further. We are not only going to predict which direction this equilibrium is shifting, but we are also going to use that with a Rice table, ooh, combo question, and figure out what our equilibrium concentration is. So, initially, 0.5 moles of each reactant and 0.3 moles of each product were placed in a 1-liter flask. So, when equilibrium is established, what is the equilibrium concentration of SO2? What is the equilibrium concentration of SO2 if we have a KEQ? Now, how do we know we need to use a Q for this question? Well, you have your given concentrations of both reactants and products. Okay, both reactants and products. How do we know that we're going to need to use a Rice table? When equilibrium is established, initially some things were placed, and then when equilibrium is established, so we weren't at equilibrium, then eventually equilibrium is established. Okay, so that's our language there. Okay, I don't know, that's not particularly a good way to notate it, but you get the idea. So we're going to need to use a Q and a Rice table, so let's start with Q. So in order to do Q, we need to have Q is equal to the concentration of SO2 initially times concentration of our other product, NO2, initially, over reactants, SO3, initial, and NO, initial. Well, our concentrations here are actually pretty straightforward. We have, let's see, it's in a 1-liter flask, so each of the products is 0.3 moles in 1 liter, so that's going to be 0.30, and because there's 2 of them, I'm going to square it. This is lovely and easy, isn't it? And now we also have 0.5 moles of each reactant, so that's going to be 0.50 squared. We do the math on that, and we get 0.3 squared divided by 0.5 squared equals 0.0. No, just 0.36, not 0.036. 0.36. All right. Now, KEQ is 1.5 times 10 to the negative 2, which is 0.015. We need them to either both be in scientific notation or both be in standard notation to do a good comparison. So Q is 0.036, which is greater than KEQ, which is 0.015. Therefore, concentration of products to concentration of reactants is too big. Therefore, we need to make this top number needs to become smaller, and this bottom number needs to become bigger. And if that happens, that whole number will become smaller. So that means we need to shift away from the products and towards the reactants, which means we are shifting left. So KEQ is greater than KEQ, Q is greater than KEQ, therefore we shift left, which means in our RICE table, we're going to be putting our pluses over on the left-hand side and our minuses over on the right-hand side. Alrighty, if you want to go ahead and do a RICE table without me, you can do that. And if you want to follow along with me, you can do that too. R. Remember your square brackets around the I and the C and the E. Those square brackets tell you that you are representing concentrations. R stands for reaction. So let's go write our reaction. SO3 plus NO. Ooh, come back. SO3 plus NO in equilibrium with, did I press start recording? I did. Okay, good. Sorry, just had a momentary little thing there. Goes to SO2 plus NO2. All right. And our initial concentrations were, my reactants were 0.50, and my products were 0.30, and we know that we are shifting to the left, which means that these have to go up and these have to go down. I will tell you that a lot of students look at these numbers and they look and they say, oh, this is a smaller number, therefore we must be shifting right. And that is absolutely not the case. It just depends on the value of KEQ, whether you need to have more products or more reactants. So don't just look at the concentrations and decide which way it's going to shift. Use a Q value to decide which way it's going to shift. All right, and equilibrium. Now, we are being asked for an equilibrium concentration, and that means that our unknown is going to be the amount of change that we get here. And these are all 1 to 1 to 1, so these are going to be changing by X and X and X and X. And then when we add all that up, we get SO3 0.50 plus X, NO 0.50 plus X, SO2 0.30 minus X, and 0.30 minus X. Excellent, excellent, ha 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 ha. Okay, now KEQ, even though the expression is technically just about the same as Q, we're going to rewrite it anyway, and it's probably going to be worth a half a mark to you, so you might as well do it. SO2, NO2, SO3, NO, and these are now all equilibrium. EQ, I should have left space for that equilibrium. You don't have to write equilibrium. It is assumed when you're doing KEQ that they are equilibrium concentrations. All right. Products. 0.30 minus X, and I have both of them the same, so I'm just going to square that. And both of my reactants are 0.50 minus X, and that's also squared, and that's equal to KEQ. And if we go back to our question, let's look for our value of KEQ. 1.5 times 10 to the minus 2. Okay, so that is equal to 1.5 times 10 to the minus 2. That makes me a little unhappy because now I'm going to have to put, in order for this equal sign to still be equal, if I want to square root everything, I'm going to have to put a square root sign over everything. So rather than doing that, I'm actually going to rewrite. I could have saved this by drawing this on a second line. 0.30 minus x squared over 0.50. Plus, look, I wrote minus, and that's a plus, plus x squared is equal to 1.5 times 10 to the minus 2. And now I'm going to take the square root of this side and the square root of that side. Okay, and this one's easy over here. We just get 0.30 minus x over 0.50 plus x. And that equals the square root of 1.5 times 10 to the negative 2 is 0.1225. That's way more digits than I need. I really only need 2, but that'll do for now. All right. 0.30 minus x is equal to 0.1225 times 0.50 plus x. And we get times 0.5 equals 0.30 minus x is equal to 0. This times this here is 0.06124 plus this times this gives you 1225x. Now we need to combine our x terms. So I'm going to bring this one over here, and that's going to give me 1.1225x. There we go. And I'm going to now combine this guy. I'm going to bring it over here, so I have to subtract it. So we have 0.30 minus 0.06124. Okay, what's that? Minus plus 0.3 equals 0.2388 equals 1.1225x. Now I'm just going to bring x over here and do the division. 0.2388 divided by 1.1225 equals, divided by 1.1225 equals 0.2127, which, well, let's see, I have an x. Oh, that's awesome. But remember, when you get an x, you have to go back and say, what did I actually want in this question? What I actually wanted was the equilibrium concentration of SO2. So go to our Rice table and look, what is the equilibrium concentration of SO2? 0.30 minus x. So, concentration of SO2, didn't leave myself much room here, did I? At equilibrium is equal to 0.30 minus x, which is equal to, and I'm going to put a line here so I don't get that calculation mixed up with this calculation, 0.30 minus 0.2127, which is equal to minus plus 0.3 equals 0.087. Now, finally, we're going to ask ourselves, do we have the correct sig figs? I rounded off already because I don't have any more room to write. So yes, we do. There's only 2 sig figs here, right? 2 decimal places because we're subtracting. And do we need a unit? Well, we're finding concentration, so yes, we do. That's going to be molar. And I'll just write this again, SO2 at equilibrium. And I will circle that puppy so that it's clear what my final answer is. And I think you are now ready to go and do the exercises for 2.3D. Don't forget, by the end of this weekend, you should have completed the exercises for all of 2.3B, C, and D. And on Monday, we will go over any questions you have. Have a great rest of the weekend.